Next speaker is Pranjal Trivedi from Hamburg University. He's going to talk about Axion-like dark matter constraints from CMB. Please.
Hello, are you able to hear me? Okay. In the beginning, a big thank you to all the organizers for the workshop and the opportunity to share with you some recent work that I've done on axion-like dark matter and how it can be sort of constrained using CMB Birefringence. Birefringence, yeah, it's a bit of a long word. It basically means the rotation of the polarization of the CMB. This is work that I've done recently with Gunter Ziegel, and we did this work in Hamburg. Dark matter. In recent years, there have been three ways in which the identity of dark matter has been investigated quite a lot. One is the primordial black holes, and this has been sort of intensified by the discovery of black holes that merge through the detection of gravitational waves. Unfortunately, the window for primordial black holes to constitute all the dark matter has kind of been closed out through various observations, including that from the lensing. WIMPs have been the dominant paradigm for dark matter, and direct detection experiments have gone through 4 orders of magnitude with no sign of the scattering of WIMPs with sort of nuclei. And indirect observations also confirm the signatures of WIMP annihilation. And at the LHC also, even though it's going to higher and higher luminosities, there is no hint of the detection of supersymmetry. So all these kind of reasons and observations force us to consider this third paradigm of axions, or ALPS. ALPS being the axion-like sort of particles. What are axions? These are pseudoscalars which were proposed to solve the problem of the lack of CP violation in the strong interactions. And they can also make up the dark matter through the mechanism of vacuum realignment, as well as from the decay of strings. The axion-like particles do not solve the strong CP problem, but they arise generically in the low energy sort of effective field theories from string theories and from those interactions which contain hidden type of those which have the sort of hidden interactions. Just to give you an idea of the landscape, so this is sort of the cross section, and this is the mass of the dark matter. WIMPs lie up over here at 100 GeV, and axions and ALPS will lie over here at micro EV to much lower masses with much smaller sort of cross sections. On this plot, we show this G, which is the coupling constant between axions and the photons, which is something of real importance when we look at ALPS as a function of the ALP mass. And here you can see this band is basically that which sort of corresponds to the QCD axion, which solves the strong CP problem. And you can see here, this is the range where you can form dark matter with ALPS. And these are the constraints from astrophysics. These are the constraints from haloscopes, and these are the constraints from experiments which look for light that can shine through walls, where the photon can go to an axion and back to another type of the photon. So when we look at the Lagrangian, the axion-like sort of particles are pseudoscalar field which do couple to electromagnetism, and this is the coupling constant of A, F, and F mu nu with sort of the tilde. G A gamma is basically so we write this as S into the alpha from electromagnetism divided by 2 pi into Fa, where Fa is the energy scale of the Pechi-Quinn symmetry breaking. And the equation of motion for the photon field can be obtained from the Lagrangian if we write down the photon field in terms of left circularly kind of polarized and right circularly polarized modes, and we get this kind of equation of motion. By the way, this is a kind of Mateo equation, which one can write like this, and one can write the Q value for a kind of galactic, density of, dark matter. One can write, the Q value as well. We will not, talk about this so much in the talk, but we'll talk about the dispersion relation that we get for the photons, which contains this additional term, which is related to, the density of the ALP field. This is the Axion field. Now, so some other authors have, written this as an A dot term. So M, which is the mass of the ALP, that goes as 1 by time. So this is like the A dot term, which has been written by the other authors. What this does is, this causes a phase difference between the left circularly polarized and the right circularly polarized, parts of light. And that phase difference we can find in terms of, the density of the Axion field or the ALP field. Here we write it in terms of, say, the galactic amount of, density. And of course, it also, depends on the ALP mass. One important thing when trying to look for this effect, when you think of ALPs making up, the dark matter on the large scales in the universe, is what is the coherence length of the ALP field. So the coherence length of the ALP field in one patch is roughly the de Broglie wavelength of the ALP. So the coherence length goes as 1 by the ALP mass and the velocity of the ALP. What this does is it gives us a certain mass scale for the ALP, which we can identify as the coherence length of the ALP field is equal to the Hubble radius at the epoch of interest. For us, that's the epoch of recombination, which is a very low kind of value of 3 × 10 to the power minus 25 eV for these sort of parameters. And these are the parameters from the recent from Planck. This is the velocity of cold dark. This is the CDM velocity at recombination, basically from the amplitude of adiabatic perturbations. And this is the this is of course the redshift of recombination. So with this, we can set basically a kind of coherence length for the ALP field, which is dependent on the ALP mass. So the calculation that we do is that you have the polarized light from the CMB, and this is a kind of schematic way of showing it in a way. We have in the polarized light from the CMB at the redshift of 1100 going to us at redshift of, and it intersects these sort of areas which have a coherent Axion field or ALP field, and in each patch there is a random amount of rotation of the polarization of the CMB. So each patch will induce a kind of birefringence angle of some delta alpha, and what we will observe is basically a random walk in the birefringence of the CMB, due to the fact that dark matter is made up of this oscillating ALP field, and the ALP field has a certain amount of coherence length, so it remains sort of coherent on a certain sort of length scale. We did the calculation, and I'll now skip to the results. We compared the results to what are the limits on the observed birefringence angle of the CMB right now, and it's about 1 degree going down to about 1/3 of a degree. Planck has a thing of about 0.6 degrees. So we took the observed upper limit on the birefringence is 0.5 sort of degrees. And it's important to note that in sort of the future, the observations of the CMB from the ground or from space can reduce this by about 2 orders of magnitude. So we were able to calculate the phase shift, and this phase shift, so this is sort of the phase shift, which is twice of the birefringence angle, and using that we can invert it to basically put an upper limit on sort of the coupling constant between the axions and the photons. And this is a value which is very small, 10 to the minus 17, for an ALP mass of 10 to the minus 25 eV, and it has these dependencies on these. So sort of other parameters. This is using this value of 0.5 degrees as the amount of birefringence that we see sort of averaged all over the sky. This is valid over the multiple range of the CMB experiment. So let's say 1 to 1000, which is basically like an Alp mass range. And that Alp mass range is basically given by this, just from the angle you see on the sky and how far you are from the distance to, basically like the distance from here to recombination. These constraints we plot on this diagram, or the coupling constant versus the Alp mass over here. And so in this part, you can't see the colors so well. So in the lighter red, you have the constraints from all the dark matter from here to recombination. And here in the dark red, we have like a subset kind of case, just for a kind of sort of comparison, where we just consider the Alps forming the dark matter just for our galaxy. So this is like the galactic case. And you can see here that basically there is there's a typical Alp mass scale of 10 to the minus 25 eV, which is basically sort of the coherent scale, which is sort of given by recombination, and here it's sort of given by the size of the galaxy. Below this, sort of the constraint goes as m to the 1, so g goes as m to the 1. This is while the light is basically going inside a patch, and only one patch of the coherent Alp field. And above this scale, you can see that the constraint goes as g proportional to m to the half. This is where the light is basically doing like a random walk through the Alp fields. That's why you have the different sort of dependence. Constraints are many orders of sort of magnitude more strong than the constraints. And you can see that for sort of the cosmic case, the range of Alps that we can constrain is 10 to the minus 27 to 10 to the minus 24, whereas for the galactic case, if we could see just the galactic part of the signal, or if you could isolate it using the anisotropy that it will induce, that range is 10 to the minus 25 to 10 to the minus 22 from here to here. How do these sort of compare with the other constraints on Alps and how they interact with the photons? So this is like they're like the same constraints, but on a much larger mass range. So you can see here, this is the band which you get for the QCD axion, and this is the band where you get sort of dark matter, which is Alp dark matter formed in the temperature dependent way. You can have Alp dark matter also in the temperature sort of independent way, which has a sort of mass limit over here, let's say. We can see that our constraints basically explore a part of the parameter space that has not been sort of constrained so far. And when you compare it to the X-ray sort of limits here, they are several orders of they are stronger by about 4 orders of sort of magnitude at this mass range. These constraints are from haloscopes. These constraints are from helioscopes that look at the sun. And these constraints are from the light shining through the wall experiments. And these constraints are from the X-ray observations. So maybe I can talk a little bit about that. Berg et al. Have put constraints from observations of one AGN in the Perseus cluster, where they assumed a 25 microgauss magnetic field in the middle of the cluster. In these constraints, they don't assume that the Alps make up all of the dark matter. This is kind of insensitive to the dark matter, which is why their constraints are flat, like as a function of Alp mass. But they do have to assume some value of the magnetic field of the cluster, and their constraint is 10 to the minus 12 GeV, which on this diagram was over here. So you can see that we improved by quite a large amount. Let me briefly mention that there have been constraints due to the cosmic birefringence from radio galaxies. In fact, this was the first work from the 3C radio galaxies back in 1990, John Carroll et al. And recently there have been articles where you can probe basically the Alp field by looking at the polarization of jet clumps of AGN or protoplanetary disks. I would emphasize that looking at the CMB will avoid all the astrophysical uncertainties that you have when looking at these kind of objects, where you want to look at basically the AGN jets or the protoplanetary disks. I should also mention that the SKA2 will also be able to measure the cosmic birefringence, because it will have a large number of radio sources with the polarization going out to an effective Lmax of 700 and a birefringence angle of 10 to the minus 2 degrees. One important thing to kind of remember is that the amount of dark matter you can put in ALPS has been sort of constrained with other probes. Basically, it can be constrained via the CMB in terms of the power spectrum because of isocurvature and so the tensors. So here you can see that in this mass range, the constraint is about 5% or so, but there's a window of these masses where the ALPS can still be all the dark matter. And it can also be constrained using observations of the Lyman alpha, where you don't see the suppression that you would expect if you had these ultralight axions. So our constraints, so if you were to say that, so we assume that ALPS are all the dark matter. If you were to say that ALPS are only 5% of the dark matter, then our constraints will weaken by a factor of 3 or a factor of 10 if the ALP dark matter fraction goes down to 10 or 1%. However, you can see that, you can see that our constraints will change only by a small amount as compared to the many orders by which they improve the existing constraints. And I'm running out of time now, so basically I'll say, these are some things which we can talk about maybe in sort of the question answer. I'll just make one last thing that there's been a lot of interest also in exploring the birefringence from axions in the laboratory. And this is quite interesting. There's an experiment to probe it in the laboratory where you can probe larger axion kind of masses, ALP masses of about 10 to the minus 13 to 10 to the minus 15, as well as axion interferometry that has been proposed by using a gravitational wave interferometer, but now using it with circularly polarized light. Summary, axion, so the oscillating axion-like dark matter leads to the birefringence or the polarized radiation, and we're able to put strong constraints, and CMB-S4, core, and SKA2 can all improve our constraints, and those are these kind of dashed lines over here by 1 to 2 orders of magnitude, and basically this helps to kind of narrow down the parts of the parameter space of the axion dark matter. Thank you very much.